Hello and welcome to week 3. This week we're looking at igneous rocks. So this is the first video lecture in week 3. Let me just go to share my screen. Whoops. Okay, so we're going to start out by thinking about igneous rock classification. Remember where igneous rocks are on the rock cycle. It's when molten material or magma cools and crystallizes to make igneous rocks. And here we have a beautiful artistic rendition of the rock cycle. We've got our molten material and the cooling and solidification or crystallization of that molten material to make igneous rock. And I'm hoping you'll remember that igneous rocks get divided into plutonic or intrusive rocks. Those are the ones that form down below the Earth's surface, and volcanic or extrusive ones. That's when the molten material reaches the surface or very close to the surface. And I'm hoping by now you start to appreciate all these gray areas in geology that can be quite annoying to people. All right, so how do we make an igneous rock? So whatever it starts from, if there's something solid, that has to be melted. And depending on the composition of that solid stuff, it'll be melted anywhere between 700 and 1200 degrees Celsius. If you want kind of a check on things, if we go down to about 100 kilometers below Earth's surface, the temperature ranges from about 1200 to 1400 degrees Celsius. So we've made our molten material, and then we have to cool it. Now, this is where it gets really exciting, because that molten material either ends up cooling slowly or cooling quickly. So just do a little thought experiment now. Where will the rock cool more slowly? Either deep down, so here I mean anywhere below 5 kilometers below the surface, or at or very close to the Earth's surface. What are you thinking? Where will it cool more slowly? And maybe why? Okay, now, so if we are deep down, the rock will cool more slowly. The reason for this essentially is that it is much harder for that cooling material to lose its heat, so it cools more slowly. Whereas if it's at the surface, the difference in temperature is greater and it cools much more quickly to make the volcanic or extrusive igneous rocks. So we've talked about where there's slow cooling and where there's quick cooling, but what about which type of igneous rocks will, oh, this is terribly written. So I want to know, will quickly cooled material have larger crystals, or will slowly cooled material have larger crystals? What are you thinking? Well, let's take a look. So here it's stated much more clearly. Where will mineral crystals be smaller versus larger in size? So if we have cooling slowly deep down, that will generate larger crystals. And that's because they have more time to grow these individual crystals of minerals. Whereas if we've got material at or near the surface, and it cools much more quickly, it basically just doesn't have time for the crystals to grow large. They get locked in at a very small size. So now, the next thing I want us to think about is the word texture. Now, texture in geology doesn't mean the way things feel. A lot of people will say, oh, something feels smooth, something feels rough. No, the word texture in geology, when we're talking about rocks, means it's all about the size and the arrangement of minerals or particles, if you want to say, in a rock. So this has to, well, this can be described as first of all, there's the size. So in the sample we're looking at here, we can see relatively small crystals. There's actually a few tiny little bits of olivine. They're the tiny pale green specks. And maybe there's a few little white needles, but it's really hard to see any crystals. This is a fine-grained rock. Every crystal of every mineral is less than 1 millimeter. We, of course, have a fancy word for that. It's called aphanitic. When we see small crystals, we know that the rock has cooled more quickly. On the other hand, moving over to the one on the right here, we've got some larger crystals. They are distinct. We can kind of pick out these elongate shapes. This is called being coarse-grained. So they are, in this case, larger than about 1 millimeter. And our fancy word for an igneous rock made of larger, coarse grains is phaneritic. And this tells us that it cools more slowly. All right, so we know about quick and slow cooling. We know about texture. If we're thinking about the recipe for making igneous rock, there's one thing we haven't thought about. What about the start of that melting process when we're first melting the rock to make the magma? If we melt a bunch of different composition rocks, then we have different compositions for the magma. And that's going to impact what is produced when that molten material cools. So here we have rocks that are formed from essentially 3 different magma compositions. And we'll look at their names later. Don't worry about that. So next up, let's think about how we actually classify rocks, or igneous rocks rather specifically. So we use their composition, and in this case I'll say, oh, that's their chemistry, and their texture. So I'm going to switch to the document camera now, and we're going to do a simple classification. So let's imagine that right here we have Earth's surface, and everything below Earth's surface is intrusive, or we use the word plutonic. And then above the surface, up here, this is where everything is called volcanic or extrusive. Now, on the scale going from left to right here, I'm going to say that everything over on the left-hand side is what we call felsic. And that's essentially a fence, that's F-E-L-S-I-C. And essentially that means that it is rich in silica. Remember, we talked about those S words last week. Over on the right, and I'm going to do the simple version here, everything is called mafic. And essentially that means it is iron and magnesium rich. So once we've got that part, I'm just going to do 3 boxes down here. And over on the left-hand side, we have the molten material that makes what we call a granite. This is the most felsic of the intrusive igneous rocks. Over on the right, we've got a gabbro. Now, there's something else I forgot to add to this diagram. Generally, once you're on the felsic side, we're dealing with pale colored rocks. And you'll learn about the exceptions in a moment. On the right-hand side, we're looking at dark colored rocks, sort of blacks and dark greeny gray colors. So granite is paler and gabbro is dark colored. And then in between is what I call, well, technically it's called a diorite. I always think of it as a Dalmatian rock because it has minerals that are pale and minerals that are dark. And just like Dalmatian, sometimes it has more dark minerals, spots, sometimes it has fewer dark minerals or spots. So that's intrusive igneous rocks. Now, if a molten material that is the same composition as gabbro reaches the surface, it makes a basalt, and that is also dark colored. If the granite reaches the surface, or not a granite, but a granitic composition molten material, that makes a rhyolite. And then we have a in-between rock. And this is the goofy one. This is andesite. So it has an overall dioritic composition. And we'll come back to why it's kind of goofy in a moment. So there are a couple of other almost groups in here. So a basalt, if it has, actually, we don't need this one. I've made an error there. If the basalt has little air bubbles in it, we call it scoria. If a rhyolite has air bubbles in it, it is a pumice. And if the rhyolite cools so quickly that it makes volcanic glass, it is obsidian. Now, there's a few funky things here. First of all, let's think about the obsidian. It isn't pale colored, it's dark. That's because it cooled so ridiculously quickly that any impurities in it were just frozen in. It is volcanic glass. And the presence of those impurities mean that the light can't move through it. You know, we're used to looking at window glass, that is pure silica. Obsidian has a bunch of other elements that are mixed in with it. Now, I'm going to ask you to look at your samples now and see if you can figure out which goes where. So just pause this and see how you do. Here we go. I'm going to put the samples down now. So okay, so the rhyolite is up here. It is usually a pinkish color. Now, depending on the sample that you've got, your sample 14 is granite. You will also see some pink minerals, that's your potassium feldspar, and there's quartz and some plagioclase in there. Diorite, this is a Dalmatian rock, number 16. And then number 18 is your gabbro. And you can definitely see that it is much darker. And the basalt, number 17. And then we look at andesite, number 15. And it actually turns out that your andesites aren't particularly good examples. Most andesites have a texture where there's crystals in them that you can see with your naked eye. They may be feldspars, they may be amphiboles. And the weird thing about andesites is, well, wait a minute, why are there some large crystals in here? The whole classification system, why are they there? Well, that's because if you imagine you are in the Andes, sitting on the chain of Andean volcanoes. Down below, there is a magma chamber. There are some crystals growing. And one thing about andesites is they're associated with explosive eruptions. All the crystals that have been growing in that molten material basically hitchhike a ride with that fast-moving magma up to the surface. And then they are locked into the otherwise fine-grained material that crystallizes at the surface. So that's your basic classification. I should say sometimes the mafic rocks get referred to as basic. That's kind of an old-fashioned term, but you might see it in the literature. There's also your number 19. It is called a peridotite. I'm just going to write that, peridotite, and it is actually ultramafic. And that means that it's got even less silica than the gabbro and basalt. It's what's associated with, or is what mantle rocks are made from. So if you think about the pizza slice of earth, this is what is in the mantle. And this is actually a pretty not very good sample. So that's our classification. We're going to go back to the slides now to think a little bit more about how we classify igneous rocks. So let me do that. All right, so we've done our classification diagram and you've messed with your rocks. Now let's just review what we've talked about. We've talked about the terms mafic and felsic, and then the in-between area or intermediate rocks, that's the diorite and andesite. Those are called intermediate rocks. And this is a version of what I just drew. And on this, I've actually shown the peridotite, and this is, I'd say, this is very obscure. Don't worry about the komatiite. Those are really weird rocks, only found very rarely. But you will see the word peridotite for mantle rocks. Okay, this is that same diagram with different rock types as images. What's missing here is a scale. I'm sorry about that. They are all at very different scales, but you know that for the gabbro, diorite, and granite, all of those distinct, different colored minerals, the crystals of the minerals, are all larger than 1 millimeter, with the exception of what you see in this andesite. The crystals in the rhyolite and basalt, all less than 1 millimeter. And we've got our little air bubbles or vesicles in the scoria and pumice. So there are actually a bunch of other ways that we go about classifying igneous rocks. And I'm actually going to go to a document here that's you have access to. It's a Word document. And it goes through how we classify igneous rocks. And we're going to just go down to geochemical composition. And so what it says here is based on the percentage of SiO2. So one thing that geochemists that study igneous rocks do is basically get a good sample of igneous rock and make sure it's not weathered or altered. They pulverize it and get what's called a whole rock geochemical analysis of it. And the way that data is presented is as what we call oxides. But what's really important is you get, the computer spits out a list of what's in it. All you have to do is look at the percentage of silica. So here we're actually going from less silica to more silica. And this is different to the direction on that classification I drew out. So if there's less than 45% silica, it's called ultramafic. There's between 45 and 52% silica, it gets called mafic. And I've put some other kind of old-fashioned words, melanocratic, mesocratic, leucocratic, in there. You may come across that in your reading, particularly some of the old descriptions of some Minnesota rocks. But you can see what's in each of these columns here. So you can now actually go to a chemical analysis and you can tell me whether the sample is felsic, intermediate, mafic, or ultramafic. And you could say, oh, if it's mafic, it would either have to be a basalt or gabbro, and then you would ask an intelligent question, which would be, how big are those crystals? So that's the geochemical approach. There's some far more sophisticated classifications that have to do with the relative proportion of different minerals. And those diagrams are included on this handout. And I'm going to scroll down to them in a moment. So geologists use a lot of what we call triangular diagrams. And that's where we consider the composition of whatever we're interested in terms of 3 components. In the case of this classification, which I do not want you to sweat over, but I do want you to know that it exists, because a lot of the terms here are terms you may hear geologists using. So in this case, A stands for alkali feldspar, Q for quartz, and P for plagioclase feldspar. So we're saying if we look at the relative percentage of those 3 minerals in a rock, these are the different names that get used. So up here, we've got almost 100% quartz. Over here, we've got 100% alkali feldspar. And to the right, we've got 100% plagic clays. And then we go down here, and there are a bunch of really ridiculously weird and relatively rare igneous rocks that don't have that much silica in them. And then there's a whole bunch of classifications for ultramafic rocks. And I've put them in here so that those of you that may already have run into these terms can see how they're organized. But don't please lose any sleep about that. Now, let's go back to the slides for a moment here. So going back to the slides, here we are. We've got percentage of silica. So you can look at this slide and you could just tell me how to classify each of these 6 igneous rocks. And, you know, look down here. The totals are close enough to 100. These are pretty good analyses. I'd be perfectly happy to use one of those in any kind of a report. So, the last thing I want us to think about is there's a whole bunch of terminology used for the different shape of intrusions. And you've probably heard of the Sierra Nevada batholith. Basically, it's a whole bunch of igneous intrusions that have amalgamated. They are, some of them are very different in composition. A batholith is actually made up of plutons and stocks. They're smaller bodies, and they may be anywhere from 1 to 10 or 20 kilometers across. So the batholith is the sort of whole body of a wide range of different plutons. Same thing happens in Minnesota. We have a bunch of plutons or stocks that have distinct mineralogy, chemical characteristics, but they all make up something we call the Central Minnesota batholith. The rest of these terms are things you can read about in the textbook. I want you to now look at this cross section. This is a vertical slice, and imagine that you're just walking along the surface here. There's a bunch of units that have been identified, B and then A. They are both part of a batholith. F is the conduit that's feeding this volcano on the surface. This weird sort of lozenge shaped thing is, it's hard to see exactly how it's fed from below, but it's igneous material. Then you've got C, which is cutting across all these other layers, and then D, which is parallel to the layers, and then E is on the surface. So what might these be named? You may be familiar with some of these terms and how to use them. If you are, stop and just test yourself. Otherwise, so we have a pluton and a stock, which make up a batholith, and often laccoliths are associated with them. Laccolith is kind of an old-fashioned term. Neck is that pipe or conduit that was feeding the surface volcano. Basalt on, well, it's usually basalt on the land surface. That's a flow. If you have material that intrudes parallel to other sedimentary layers, we call it a sill. And if that intrusion, the may reach the surface, cuts across the other layers. It's called a dike. So with that, we've looked at a general introduction to igneous rock classification. Thank you.